Hi everyone, welcome back. Let's write some more Leetcode today. Today we are solving count the number of complete components. So the problem states that we are given an integer n, and there's an undirected graph with n vertices, and it ranges from 0 to n minus 1. And we are given a 2D integer array edges, where at each edge it will have two elements, and the two elements denote that there is an undirected edge connecting the two vertices. And we want to return the number of complete connected components of the graph. And a connected component is a subgraph of a graph which there exists a path between any two vertices, and no vertex of the subgraph shares an edge with the vertex outside of the subgraph. And a connected component is complete if there exists an edge between every pair of its vertices. So if we look at this example, we will return 3 because 5 makes a complete connected component, 0, 1, and 2 makes another complete connected component, and 3 and 4 itself makes another complete connected component. So we'll return 3. Now that we have seen some examples, let's get to how we can solve this problem. Before we get to how we can solve this problem, we should acknowledge that for a complete connected component, its number of vertices times vertices minus 1 divided by 2 should equal to its number of edges. If that is the case, then we know it's a complete connected component. But for this example, since we're using an adjacency list, we will use this to see if we have a complete connected component, which we'll get to later on. So what we will do is we will create an adjacency list, which will have its vertices match with all the other vertices that it has shares an edge with. And we will look through every node from 0 to n minus 1. And as we look through each node, we will look at how many vertices is in that subgraph and how many edges is in that subgraph. And based on these two info that we collect, we will check if the number of vertices times the number of vertices minus 1 is equal to the number of edges. If it is, then we increment the result by 1 because that means we have found a complete connected component. And as we search through the nodes, we want to keep track of visit, meaning that as soon as we get to a node, we want to add that node to visit. So as we search for the nodes later on, it will not repeat itself. So let's go through this example real quick. So we can start at node 0. And we see that node 0 has node 1 and node 2. So then we will look at 1 and also node 2. And we see that these three shares a subgraph. So we will collect the info. Node 0 has one vertice and it makes two edges. Node 1 has one vertice and it can make two edges as well. And node 2 has one vertice and it can make two edges as well. So as we can see from the info we collect, we got 3 vertices and 6 edges. And if we do 3 times 3 minus 1, which is 3 times 2, it does equal to 6. So that does make a complete connected component. So we can increment the result by 1. And we have visited these 3 nodes. So we put 0, 1, 2 in visit. So they do not repeat. So now we look at n equal to 1. We already have visited. So we can skip. And we can skip 2 as well since we have already visited. So now we are at 3. And when we get to 3 and 4, we realize that there are 2 vertices and they can also make 2 edges combined. And 2 times 2 minus 1, which is 2 times 1, it does equal to 2. So that is a complete connected component. So we can increment the result again to 2. And we want to add 3 and 4 to visit. So now we look at 5. Since 5 originally was not in the adjacency list, we will just add 5 with an empty array inside. So we realize that it has one vertice and it makes 0 edges. 1 times 1 minus 0, which is 1 times 0, it does equal to 0. So that is a complete connected component. So we can increment the result again, and that is 3. And we have reached the end of the nodes that we want to check. So we can return 3 as our result. And the time complexity would be O of E plus V because it will depend on the number of edges and vertices. And the space complexity will also be E plus V because the adjacency list will depend on the number of edges and vertices. So now let's get to the coding part. So first we make the adjacency list default dict list. And for vertice 1 and vertice 2 in edges, we would append them. So adjacency of V1 append V2 and adjacency of V2 also will append V1. And for the result, we'll initialize to 0 and visit will start with an empty set. And now we will first write our search function, so cur and info. So we want to add the node, which is cur, visit.add cur. And info, the vertice of 0, will add it by 1. And the second one is the number of edges. So we want to add by the length of the adjacency of the node. So adjacency of cur. And we want to look at its neighbors inside that node. And if we have not visited yet, then we want to search through that. So DFS neighbor info. Yeah, so now we can get to the main function. So for the vertex in range n, if we have not visited, then, or if we have visited, then we want to continue. If not, then we can initialize the info to 0 and 0. And we want to search through the vertex with that info. And in the end, if the info of 0, meaning the number of vertices, times the number of vertices minus 1 is equal to info of 1, meaning the number of edges, then we can increment the result by 1. And then we can return result in the very end. See if it works. Okay, perfect. Hope this was helpful. I thank you all for watching. If you have any other questions or comments, feel free to leave it down in the comment section, and I hope to see you all again soon.